And just time me because I might take a little bit more than 15 minutes. So as I was telling you today, I'm going to present the substitution.
Okay.
Yes?
Just so you, I'm sorry to interrupt.
Oh, yes.
Just so you know, we'll stop you at 15 minutes.
Excellent.
Okay, great.
So, today I'm going to present a very short lecture about the substitution rule for integrals. And right now, the main motivation for me to present this rule is that I am interested into integrating this function. And so probably, you already know how to integrate this power function, the integral of 3 times x plus 1 to the square dx. And one thing that you can do is you can expand x plus 1 squared. This is a perfect square, and then you can integrate each term one by one. But maybe, we can do like a little bit of a wild guess, and we can speculate, and we can say right away that the integral is x plus 1 cubed over 3, and since we have this 3, this is going to cancel out, and then I'm going to add the integration constant. Right now it's a little bit of a wild guess, but the interesting thing about just integrating these functions...
Christian?
Yes?
Christian, may I interrupt for a moment? I can't see your presentation.
Oh, I'm sorry. I needed to share the screen to you. Oh.
That's okay.
Okay, so I'm just going to erase, yeah. Yeah, okay, so at least, I didn't do too much. So, I want to integrate this function, and oh, well, I erased the 3, but that's fine. I'm going to work it without the 3. So right now, you can expand this function, and then you can integrate each of the terms. But I think it's just easier if we just do like a wild guess and provide this as the integral of this function. And at least, we can verify our answer, because if we differentiate this function, we're going to find out that the derivative of that antiderivative is just 3 over 3 times x plus 1 squared. So we get to the same answer. And right now, we haven't formalized this rule at all, but it is giving us some motivation to integrate functions that are going to have way longer expressions. So over here, you can expand this polynomial, but it is going to take so much time. And then, you might even be interested into integrating something like this. And over here, you have something more interesting. You not only have to expand, but you also have to take care of this term 2 times x. So how can we formalize this rule? What we can do is we can recall the chain rule for differentiation. So right now I want to find the derivative of g of x to the n plus 1. I am just using a power of n plus 1, so we get a much simpler derivative. And I also am going to divide this function by n plus 1. And then, if I take the derivative of this function by using the power rule, the n plus 1 in the numerator is going to cancel out with the n plus 1 of the denominator. The power of this function is going to decrease by 1, but I also have to take the derivative of the inner function. And this is providing me quite a nice motivation into finding the integral of this function, because over here I have the antiderivative, and over here I have the derivative of the antiderivative. So right now what I want to say is that I want to integrate this function. I want to integrate g of x to the n times g prime of x dx. And since the derivation and the integration are reverse process, we can say, okay, by integrating this function, we get this antiderivative. And with this, we are starting to formalize the substitution rule. But why am I talking about a substitution? To visualize this rule in these terms is a little bit hard. So what you can do instead is propose a new variable that is going to be defined in terms of g of x, and then you're going to take advantage that the derivative of g of x is just outside of this power function. Du is equal to g prime of x times dx. And if you use this substitution rule, then this integral is going to be much easier to visualize. And then if you already see this function, you can integrate it without any problem. U to the n plus 1 over n plus 1. There is just a small reminder that if you have u to the minus 1, that rule has its own the integral. And then basically this is the purpose of the substitution rule, to find a much easier visualization of a function that you want to integrate. And basically, I'm going to do a few examples. Maybe I'm just going to have enough time to do 2 or 3 examples. So we're going to integrate the following functions. So I'm going to start with this integral that, you can still do it theoretically by taking this power of 5, multiplying by 2x and integrating each of the terms, but it's just going to take so much time. So the one thing that the substitution rule is not telling you is what is the variable of substitution. So pretty much you have to scan your integral and see which function you're going to use as the substitution, and if the derivative of that function is somewhere else in the integral. At least in this case, we're very lucky, because if we propose that u is equal to x squared plus 3, then the derivative of this function is equal to 2x times dx. So pretty much you can already replace this composite function with just u to the 5, and all of this is going to be the new differential. So one thing to keep in mind is, if you're proposing a new variable of substitution, that the old variable has to completely vanish, otherwise the substitution is not a proper substitution to use. And then you just use the power rule, u to the 6 divided by 6 plus a constant. But then you have to keep in mind that you have to return to the original x variable. But the nice thing about using this substitution is you already have integrated this function. So we just replace u with x squared plus 3 to the 6 divided by 6 plus an arbitrary constant. And in this problem, the substitution rule is the only way to integrate this function, because now we're going to integrate a function that has a fractionary power. So all of this expression is elevated to the 2/3, and we really can expand that fraction. And another small issue that we're going to have to deal in this problem is that the variable that we're proposing, the derivative is not going to be exactly there, but we can always do the substitution as long as we multiply or divide by a proper constant. So over here, I'm just going to propose that this is going to be my variable of substitution. And then I'm going to take the derivative of all of these functions. So this is equal to 3y squared plus 6 times y plus 0. And then I'm going to multiply this by dx. And I think with this problem I have, then you just erase these 3. You need y squared plus 2y, otherwise this function would be impossible to integrate. So what you're seeing right now is that we don't have exactly over here 3y squared plus 6 times y, but basically, if we just divide this du by 3, and There are other ways you can find what is the right constant, so you can do the right substitution. Over here we finally have that all of this term is going to be replaced by du over 3. So this is something that we're going to have to do in some of the problems. So we have u to the 2/3 times du over 3. As long as you're multiplying or dividing by a constant, this is a proper substitution. And then I am just going to integrate. With this power rule, I have to increase this fraction by 1, so this is going to be 5/3. And then I divide this by 5/3, or I can just multiply it by the flipped fraction. This is a way nicer way to visualize the final integral. And then I am just going to replace u with the original y variable. I think I only have time for one more problem. So with this problem I'm just going to mention that you can also use the substitution rule for any composition of functions. It is not only limited composition of functions. So this is not only limited to power functions, you can also integrate functions that look like this. But the key is to find, the right variable of substitution, and the derivative of this new variable of substitution has to be elsewhere in the integral. So one problem that I can do, let me just do this one. The one with the exponential function. So this one is a little bit trickier, but basically, we just have to keep in mind that, okay, the derivative of e to the 1 over x, we don't have it elsewhere in this problem. But what we do have is that the derivative of 1 over x is equal to minus 1 over x squared. And this is exactly what we have over here. We just have to deal with a negative sign, but that is really not a problem. If you really can see that this is going to be minus negative du, what you can do is you can solve for dx. It's something that I don't particularly like, but probably it is going to help you visualize more easily what is the right substitution. And then I am just going to replace 1 over x with u, and then we're going to have this a little bit of unnecessary step, but you can do it. Minus x squared times du over x squared. You're going to notice that these x squares are going to cancel, and then we're finally with just the integral of the exponential function. So the integral of this function is e to the u plus c, and then I just replace u with 1 over x. And I think I can still do one more problem. Okay, I have just a couple of minutes, but with this problem, I can really give you a big picture of why the substitution rule is so critical. As you already know, you know how to integrate sine, cosine, secant squared, cosecant squared, secant x times tangent x, but what about cotangent x and tangent x? Now we can finally integrate these elementary trigonometric functions. The only thing is we have to be a little bit more clever with this problem. We have to remind ourselves that cotangent is equal to cosine x over sine of x. And over here we have to be careful. Our u is not cosine because the derivative of cosine is sine, and what we have over here is not sine times dx, it is dx over sine x. So actually what is the substitution that is going to help us here is that u is sine of x, and the derivative of sine is just right on the numerator. So all of this is going to be du over u, and then over here we're with the exception to the power rule, the derivative of u to the minus 1 is the natural logarithm. I'm just going to add the absolute value brackets because, as you know, the logarithm of the absolute value has exactly this derivative either for positive numbers or negative numbers. And then finally, I'm just going to replace u with sine of x. So this is the integral of cotangent of x. The integral of tangent is going to be very similar, and we can just do a lot of these problems using the composition rule as long as you happen to find that u and its derivative is over there. Now, just as a warning, we have to be careful with this rule because this rule is very powerful, but you are not going to be able to use it if you want to integrate functions like this. With this one, the substitution rule doesn't work because the derivative of x is 1 and over here we have an x squared. With this one, we are also not going to be able to use the substitution rule because the derivative of 1 minus x squared is absent from this integral. But still, you know, we're going to integrate these two functions with new integration techniques. But the funny thing is that both of these are still going to be based on the substitution rule. Thank you very much.